backside of 6.2 notes, we are talking about scales and scale drawings today. A scale drawing is the same shape as the object it represents. Fill in your blank. Scale drawing. What is an example in real life of a scale drawing? Blueprints, maps, a globe, instructions. Oh, like when you find the instructions to put together like a piece of furniture? Yeah. Atlases, yep. A scale drawing is the same shape as the object it represents, and on a map, on a blueprint, on the instructions to assemble a piece of furniture, we often, 99% of the time, you have a scale. If you don't have a scale is a ratio relating the dimensions in a drawing to the actual size. So, like when you look at a map, what's an example of a scale? Raise your hand and tell me. What's a scale tell you? What's it look like? How do you find a scale? Raise your hand and tell me. Exactly. 1 inch to so many miles, right? It's always like it's typically 1 inch. You might see 1 centimeter to so many miles or kilometers, right? So check this out. The length of a key in a scale drawing is 7 centimeters. The length of the actual key is 4 centimeters. We want to know, well, what's the scale? I'm giving you these two numbers, and on your paper, highlight them. In our scale drawing, the key is 7 centimeters. In real life, the actual key is 4 centimeters. So we underline the information we have, and then before we write our scale, you need to know this about a scale. Make sure you get this down. This is part of your notes. A scale always takes the model and it compares it to the actual. So like the dimensions in the model is compared to the actual. So like 1 inch on your map, on your model, compares to how many miles in real life is what we're doing. So in this case, in my model, my scale drawing is 7 centimeters. But really, actually, in real life, the key is only 4 centimeters. Doesn't very often happen that you have a model that's bigger than your actual real life figure or whatever it is. But in this case, we do. So what do we say? It's always 1 inch, 1 centimeter, 1 something equals so many other units. How do I turn the 7 into a 1? How do I get it to be a 1? Divide by 7. And if I divide the top by 7, I divide the bottom by 7. 7 divided by 7 gives me 1 centimeter in the top. And in the denominator, in the bottom, 4 divided by 7 is 0.571. We'll go 0.57, and we have centimeters. What happens if you have centimeters on the top and centimeters in the bottom? They basically cancel each other out. So what do we have? We have 2.57. In the model, it's like 1 unit compared to 0.57 times as big for your model. So here's what happens. When you look at this is kind of like what's called your scale factor. And I haven't talked to you about that yet, but this is a new concept and we're going to work with it quite a bit more. From the model to the actual is 0.57 times as big as what the model is. The actual is 0.57 times as big as what the model is. So we've been talking about this first I can statement. I can write and solve proportions to solve problems. The second one is where I'm starting to introduce you to the next I can statement. We're not going to go there too much, but the second one says I can use proportions to identify similar polygons. To identify similar polygons, we need to know about our scale factor. And that's what I'm showing you right now. Example 4. You buy a 3D model of the Sun Sphere in Knoxville, Tennessee. The actual building is 266 feet tall. Your model is 20 inches tall, and the diameter of the dome on your scale model is 5.6 inches. Hold on a second. Anybody ever been to Knoxville? No? I haven't. The actual building is 266 feet tall. I'm like looking at my information, pulling it out. What do I have? Actual building is 266 feet tall. Model is 20 inches tall. The diameter, now I'm changing gears a little bit. The diameter on the scale model is about 5.6 inches. What's diameter? It's not around the circle. Around the circle is called your circumference. It's the distance all the way across your circle, or across your sphere. The distance all the way across the circle is called the diameter. Distance around is circumference. And halfway across is called your radius. Good, good, good. So here it says, what's the diameter of the actual dome? If we're dealing with like two different units, what do we need to set up? We need to write a proportion, right? So we set up a proportion, and then we need to label stuff so we know exactly where everything goes. The actual building is 266 feet tall, and your model is 20 inches tall. So I've got the actual building, and I have the model. And like I told you before, it's model over actual, but for right now, to write a proportion, we're okay. So the actual building is 266 feet tall, and the model is 20 inches tall, right? Those are like the heights. The diameter of the dome on your scale model is about 5.6 inches. Where's that 5.6 inches go? It's still dealing with my model. It's still in inches, right? So we put our 5.6 inches here. We cross multiply. 20 times x gives us 20x. 266 times 5.6 gives us 1,489.6. We divide by 20. And x equals 74.48. So if I round it like 74.5, and what's my units? X is on top, so up top I have feet. 74.5 feet for the actual dome diameter. So does this make sense? When I talk about how tall the figure is, it's 266 feet tall in real life, but the model's 20 inches tall. So now when I come over here and I talk about the diameter, in real life I'm saying it's 74.5 feet tall, and on my model it's only 5.6 inches for the diameter. Does that make sense? If I put the 74.5 here, does that look right? How do we tell? How do you get from 5 to 20? Multiply by 4-ish, right? How do we get from 74 to 266? Even if we round down and go 70 times 4, that's about 280. It's relatively close, right? One's 4 times as big as the other, approximately. How many times as tall is the actual building than the scale? So if I say how many times as tall, it's like looking for the scale. What's your scale? What's your scale factor? How many times as tall is the one than the other? We need to find our scale. Scale is model over actual. So what did we say before? How many times as tall is the actual building than the scale, than our model? We're talking about the height of the building. What goes up top? The model is 20 inches tall, and the actual height of the sun sphere is 266 feet. And here's that question. I want to simplify that so I can find my scale factor, so I can find my scale. Do I have the same units where I can just cross them out? No. So here's where we need to go in, and I want it to the same unit. So I'm going to multiply by, if feet are in the bottom, we put feet in the top, inches in the top, inches in the bottom. So here's where your 1 foot for every 12 inches comes in. Using your conversions right here, 1 foot for 12 inches. 12 inches for 1 foot. Feet cancel, inches cancel. 20 times 1 gives us 20. 266 times 12 gives us 3,192. To find my scale, it's always 1 to something else. How do I get that 20 down to 1? Divide by 20. Divide by 20. And we get 1 over 159.6. Do we agree? So what's the question? How many times as tall is the actual building than the scale? This is the model. This is the actual. The actual is how many times as big? 159.6 times as big. Check out this one. Two landmarks are 130 miles from each other. The landmarks are 6.5 inches apart from each other on the map. Find the scale. What do we know? 130 miles from each other. They're 6.5 inches apart on the map, on our model. How do we find a scale? What's the rule for scale? Model over actual. So what do we know? On the model, on the map, it is how big? 2.5 inches. And actually, if we were to measure it with our, I don't know how you measure it, driving it with your car, yeah, we have 130 miles. For my scale, we want it to be 1 inch for so many miles. How do we get it down to 1? Divide by 6.5. There we go. If I do it to the top, we've got to do it to the bottom to keep everything equal. 20 miles. So this is my scale, 1 inch for every 20 miles. Get it? Got it?